Welcome to the last live session of 2017 for the online course. Sorry we're a little late starting today. We're all off Christmas shopping. You know, the roads are jammed. So welcome to the last live session of, oh, there's a little echo in the room. We'll get rid of that. And very soon the floor will be open for your questions.
All right, the first question we have is about the recent asteroid that came through our solar system. And can you just talk a little bit about that asteroid and what astronomers think it is and where it came from?
Right. I'm not going to pronounce it correctly. It's Oumuamua, I think, O-U-M-A-U-M-A-U, Hawaiian word, because it was discovered in the survey in Hawaii that's going on to track moving objects. It's the same survey that's hoping to protect us from impacts by tracking and cataloging objects more than a few hundred meters across that might hit the Earth in Earth-crossing orbits. So it's an interloper into the solar system, and that's confirmed. I mean, obviously there are comets which travel, there are asteroids which come from the asteroid belt toward the Earth and near Earth. They're originating only a few times Earth orbit away. There are comets which really come from extremely far out in the solar system, tens or hundreds of times further than the orbits of Neptune and Uranus, but those are still bound to the sun gravitationally. This is an object which by its trajectory and by its velocity is not bound to the solar system, and therefore we know that it's an interloper. We know that it's been traveling through interstellar space. It originated presumably in another star system, another solar system. It's not clear where that would be because tracking or back projecting its trajectory for millennia is not a reliable pursuit, even with big computers. There's just, the trajectory is just uncertain enough that that's hard to do. But it's undoubtedly an interloper, so it's an interstellar object entering our solar system, coming quite close to the Earth, which is exciting because it doesn't happen very often. It's, for example, evidence that rocks from other star systems can come into the solar system, to the inner solar system. The idea of panspermia, the idea that microbes and life in the universe could spread between solar systems, is an interesting idea, and the presence of an object from another solar system is a reminder that this could actually happen. I mean, if there were somehow microbes buried deep within this space rock, and this rock hit the Earth, and those microbes were in the state of suspended animation, which they would have had to have had for millions of years, and apparently microbes probably can do that, then that's a mechanism for life spreading through the nearby universe. So there are a lot of issues raised by an interstellar interloper. The other peculiar thing about it, of course, is its shape. It's extremely elongated. Gravity will make anything much larger than, say, Phobos and Deimos, the small potato-shaped moons of Mars, into a spherical shape. When the rocks form by accretion in the early solar system, they're still high temperature, tacky, almost molten, and so they're viscous. The rock is viscous and can flow, and again, gravity will cause it to form a spherical shape, the most symmetric shape. And that doesn't necessarily happen for a small rock. Well, Oumuamua is a small asteroid or interloper, whatever you want to call it, but none has been observed in the solar system. No asteroid, no comet, no small space rock that is as elongated as it is. It's almost, I think it's 8 times longer than it is wide and thick, which is really quite extraordinary. So people have speculated how that could be. Did it form that way? Was it somehow extruded in an impact early on when it was still molten and it just sort of solidified into an elongated shape? Does it represent the collision of a couple of things that might have already had to have been elongated for it to be that long and skinny, almost cigar shape? And at the moment, that's a bit of a mystery about this space rock. Nobody really knows how it either formed that elongated or got that elongated by things that happened after it formed. So it's obviously exciting. It's very interesting. It's not going to come close enough for us to have the prospect of visiting it, say, with the spacecraft. There's simply not enough time to prepare a spacecraft and get to it. And it's actually on an orbit and going at a speed where that would be really difficult anyway. So we're just going to have to settle for telescopic observations, but it's a rare treat.
All right, our next question If a red dwarf replaces the sun, is it possible for Earth to receive the same amount of radiation and stay at the same temperature at its current distance, or would it need to be closer? And what changes about red dwarfs' habitable zones?
So if the sun were overnight replaced by a red dwarf, well, there would actually be several big problems. A red dwarf star, red dwarfs are essentially 10% or 15% of the mass of the sun. 8% of the mass of the sun is the limit of a stellar fusion object. So below 8% of the mass of the sun, it's just a hot gas ball, and it doesn't actually have nuclear burning, and so fusion. Let's say 10 to 15% of the mass of the sun, you have a red dwarf. Of course, you know, the Earth traveling at its current speed, if the sun was suddenly replaced by something 10 times less mass, it would just fly off into space. Imagine twirling a stone on a string over your head and the string breaks, well, the stone will just fly off into space. So the most immediate consequence of the sun being replaced by a red dwarf is that all the planets would just fly off into space. Assuming somehow they didn't do that, the radiation received by the Earth and by all other planets at their typical distances would go down a lot. So a red dwarf is maybe 10 times less massive than the sun, but it's thousands of times less luminous, up to 10,000 times less luminous. And that means that's the number of photons coming out per second. Light goes down as the inverse square of the distance, the amount of photons. So the math of that is that we would have to be 100 times closer to the sun as a red dwarf to get the same amount of radiation that we get now. 100 times closer, you can think about it, it's very close. It's 100 million turning into 1 million miles. So way, way inside the orbit of Mercury to get the same radiation we get now. And so that leads to the general idea that red dwarfs do have habitable zones. Their planets will just have to be closer. You know, an Earth-like planet will be 100 times closer than it is to a sun-like star. But at that distance, it is receiving the same amount of radiation. And so potentially, it could be habitable, meaning it's at the temperature where water could be liquid on its surface. But then you have an extra issue or an extra problem. When a planet is that close to a star, it gets tidally locked. So just as the moon is fairly close to the Earth, and the Earth-Moon interaction causes one face of the moon to always keep facing us, so we only ever see that one face of the moon, the same thing would happen to the Earth around a red dwarf. So rather than spinning around its axis as it does now as we orbit the sun, the Earth would be locked onto that red dwarf with the same face always pointing it. And so that would mean in practice that one face of the Earth would get a lot of radiation all the time, 100% daytime, and the far side of the Earth would be 100% night. So the temperature variations on that hypothetical Earth around a red dwarf would be extreme, and it might be uninhabitable completely, because it might just be both too cold and too hot. Now, an atmosphere on an Earth-like planet will sort of smears out the heat. The hypothetical temperature variations from day and night time on the Earth are, of course, smoothed out enormously by the atmosphere, which acts like a blanket. And so the same would be true on the Earth around a red dwarf, but still people think that the red dwarf environment would be very extreme, so likely less habitable than an Earth-like planet around a sun-like star.
All right, the next question is from one of our live viewers who asks, when is Pluto expected to finish clearing out its orbit?
Well, that's a very long time. So Pluto is, of course, is a highly inclined and a highly elliptical orbit. The evidence is, based on its peculiar orbit, that it was captured from the Kuiper Belt, which is the outer region of the solar system from sort of 30 or 40 to 70 or 80 astronomical units, where there's a lot of rocks out there, a number of which are Pluto-sized. And so we just think that Pluto was one of the larger of those rocks that got close enough to Uranus and Neptune to be pulled into their sphere of influence gravitationally. So in that sense, it's going to be very difficult for Pluto to clear out its orbit, because its orbit is inclined to the plane of the solar system. And most of the debris left over from the formation of the solar system, like the asteroid belt and a lot of the other space rocks, are in what's called the ecliptic plane. That's the the path taken by the sun in the sky defines the ecliptic. It's the thin sheet-like configuration of most of the planets in the solar system. So Pluto goes both in and out of that sheet, and there's not a lot of debris there. So in a sense, there isn't much debris for Pluto to clear out. And also, because it's so small, its ability to clear up debris or sweep up material is extremely limited. So the real answer to the question is, hundreds or tens of millions of years, and maybe never, because maybe Pluto can't clear out its orbit.
Right, the next question is from one of our viewers who asks, I'm thinking of going to the Atacama Desert in July. Is that a good time of year to go? I heard it's the best time of year for stargazing and seeing the core of the Milky Way. Is that true?
Yes, I've been to the Atacama 4 or 5 times, I guess, usually after observing in Chile. The observatories in Chile, the optical observatories, are in the middle part of the country near La Serena. But there, of course, is a major radio facility, ALMA, which is in the Atacama Desert. I was there last year, actually. So in general, the Atacama Desert is a good place to go. It's in July. That's obviously the Chilean winter, and it turns out that even though you're at a fairly modest latitude, it can be very cold there. So it's not a bad time to go for viewing the sky. It's actually wonderful, but it's pretty clear most of the year. You're going to need many layers and lots of clothes, because if you were down near the coast, near Antofagasta, which is the nearest big coastal city to the Atacama Desert, it would be beach weather. You'd be wearing, t-shirt and shorts. But if you go into the high plateau, which is just below the Andes, essentially, you're at 5,000 to 7,000 feet. And for some of the interesting hikes or excursions, you quickly get up to 10,000 to even 12,000 feet. And in that thin desert air, even in their midsummer, it can be very cold. And of course, very cold at night. Like in the desert where I live, the Sonoran Desert, the day to nighttime temperature ranges are 40 degrees or more. So you're going to need a lot of layers, and you're definitely going to need warm clothes for the higher elevations and the nighttime temperatures. But yes, the sky is wonderful. The winter is a great time to see the Milky Way and the best sort of star clusters and deep sky objects. And there are some small observatories that have been set up outside the professional observatories. There's ecotourism type observatories, little canvas domes where you can sleep under the stars and then walk down the road 100 meters to a telescope they've set up. And I visited one of those sites, and they're scattered through Chile. There's 4 or 5 of them, and they're excellent. They do a really good job.
The next question is from one of our live viewers who asks, when are we going to find planets 9 and 10? How close are we to finding planets 9 and 10 in our solar system?
Yeah, we're a couple of years away. The surveys that are ongoing to catalog the largest objects in the Kuiper Belt, that region of space beyond the orbits of Neptune and Uranus, so 30, 40, out to 70 or 80 astronomical units, those surveys are probably halfway through. The best of those surveys started 2 or 3, 4 years ago, and it's a big job to cover that amount of sky, because you're not just looking at a narrow strip, the ecliptic. In that far out from the sun, the objects could be considerably spread out from the ecliptic. So rather than looking just at a thin strip of a few degrees wide centered on the ecliptic, you're looking at a broad swath or a band, maybe 20 degrees wide, centered on the ecliptic. And that's a lot of sky all around the sky. And you have to go deep. And you have to look for a long time, because you're looking for very slow-moving objects at those distances. So those surveys are a few years away from being complete. They will release objects they find that are Pluto-sized or close to it as they find them. And most of the people running those surveys or working in them think they'll find a handful, 2 to 4 Pluto-sized objects, Eris, about the size of Eris, or these other larger objects in the outer solar system. And possible 1 or 2 of them may be larger than Pluto.
Right, the next question is, in this moment, can we take photos using gravitational lenses, and what kind of errors are there with this technique?
So we can take photos, but you don't have to be a professional astronomer. but you have to have a pretty significant observational capability. So I would say high-end amateur astronomers, people with, there are people with 15, 20-inch Dobbs and CCDs. Well, they don't usually track with a Dobb, but if you have a 10, 12-inch reflector with tracking capability and a good CCD, cooled CCD, thermoelectrically cooled, you can take an image deep enough to see gravitational lensing, which is to say the lensing arcs that are formed by galaxies and clusters that are mostly made of dark matter. So that's a very challenging project for an amateur astronomer, but the high-end amateurs have enough equipment to do that. But in professional circles, taking pictures of gravitational lensing is essentially routine. The Hubble Space Telescope has taken pictures of hundreds of different targets where there's lensing. And in some of these configurations with a cluster, you can see hundreds of individual background galaxies lensed. So in one picture, you can get 100 or 200 or even 300 verifications of general relativity caused by the little lensing arcs. And then from the ground base with adaptive optics, you can take similar quality from the ground. So I would say in total, there are several thousand images that show gravitational lensing. It's really a routine phenomenon now, and it's the best way we have of measuring dark matter.
Right, since it is the end of the year, what are your predictions for what's going to be big in astronomy in 2018?
Big in astronomy. Okay, well, almost safe bet is that we're going to see more gravitational waves, and probably we're going to see more of the neutron star collisions that caused such excitement just a couple of years ago. So LIGO is in its advanced phase in routinely taking data. It will have some more downtime for technical upgrades. That's going to happen every few years as they try to improve sensitivity. But LIGO is going to enter a regime where it should be detecting some sort of event, either a black hole collision, a black hole neutron star collision, or a neutron star collision, pretty much every couple of weeks. Best guesses are 30 events a year. So we can expect it to become routine. It's sort of like the situation in the late 1990s after the first exoplanets were found, when exoplanet detection started to get routine. And then with Kepler, sort of the hundreds at a time were being announced. The gravitational waves are never going to get to that point. It's always going to be hard work. So gravitational waves are just going to become a big thing, and we're going to have new tests of general relativity. In that same vein, another prediction is that the Event Horizon Telescope will, probably by the end of the year, next year, take an image of an event horizon of a massive black hole. First time that's ever been done. The Event Horizon Telescope is a interferometer working at millimeter wavelengths, so it's radio telescopes scattered around the world. One of them is in Arizona, and some of the scientists in that collaboration work at my university, in my department. And they are planning to use the super sharp seeing of the center of our galaxy, which has to be done at long wavelengths because the center of our galaxy is not visible with optical light, to essentially observe the shadowing of the 4 million solar mass black hole against background stars and gas. And that will be a direct test of the theory of gravity in a very profound way, because we've never had a demonstration that event horizons actually exist. It's a theoretical concept out of gravity theory. So I can predict that will happen. I could be really bold and say that the first experiment to detect biologically induced gases in the atmosphere of an Earth-like exoplanet happens, but that's probably pushing it. I think that experiment may be more like 2 or 3 years away. And that involves using adaptive optics on the ground. James Webb Space Telescope is now pushed off into 2019, so I'm not going to make any prediction about that because its launch has been delayed. But ground-based telescopes will be able to take super sharp images of Earth-like exoplanets, the nearest, maybe 10, 15, 20 light years away, blot out their parent star. Working in the near infrared, that contrast is a few 100 million to 1 rather than a few billion to 1, and disperse the infrared light from the reflected light of the exoplanet into a spectrum and look for oxygen, ozone, methane, water vapor, the things that on Earth would indicate life. So it's a stretch, but that experiment could potentially be done by the end of next year for the first time. So those are the most dramatic things I expect to happen in astronomy.
Great. The next question is from a live viewer, Kenneth, who asks, what is the function of the International Space Station?
The International Space Station is a proof of concept that we can live and work in space. It's taken its knocks from many quarters. Many of my colleagues, many in the space science community, question its cost and utility. I think the price tag of the space station since the mid-1980s is 120, probably $130 billion, a lot of money. And even the annual cost is significant. But it does represent one of the interesting and rare times that all the countries, all the spacefaring countries cooperate. So I think scientists and engineers and astronauts from several dozen countries have been to the space station. So as an example of international cooperation in space, it's really important. Russian and American cosmonauts are routinely together on the space station, and we're having our issues with the Russians these days. So in that area, everything is all smooth and cooperative. Chinese cosmonauts have occasionally been up there. Most European countries, in fact, many countries have had their first astronauts going aboard the space station. I'm a Brit, so the first British astronaut, Tim Peake, went up, I think, a year ago to the space station for a few months. So it's a good demonstration of that. It's also a demonstration of the ability to build things in space. The space station has grown enormously since it was first put up there, as pieces have been added, capabilities have been added, labs have been built within it, various types of equipment for working in space have been tested. A lot of that work is kind of mundane. It's like mundane electrical work and plumbing work. It's not all very glamorous, and I'm sure being on the space station for 6 or 8 months would actually get quite dull after a while. It's also been used to do long-term medical experiments on zero gravity. There are Russian cosmonauts and Americans too who have been up. The Kelly twins, one of the Kelly twins, of course, was up for a year. There are cosmonauts who've been up for 2, maybe more than 3 years. So we've learned a lot about medical science from the space station. The question is it worth the cost? And essentially, that's an argument that people will just disagree on. Some people think yes, some people think no.
All right, the next question from one of our live viewers is, did the laws of physics exist before the formation of the universe?
Good question. That's a good question because it begs the question of, was there anything before the universe? Did everything come into being at once, the physics and the universe itself? And the answer is simply, we don't know. It's a great question, though, because it's almost a philosophical question as well as a scientific question. One way to put it would be that the laws of physics are emergent properties from the universe. The other possibility, and we really can't distinguish these two, is that the laws of physics were sort of built in at the Big Bang, built into the beginning. They were essentially boundary conditions or coded into the space-time, the bizarre and exotic space-time state that was the Big Bang itself. So that's a very important question, and we simply don't know the answer to. We do know that the laws of physics are very particular. The strength of the forces of nature are very particular. The fundamental constants are very particular. And people have argued in general terms they didn't have to be that way. You could have physics that's not our physics. You could have different physics and it would still be physics. Things would make sense. Causality would hold. There would be a scientific method. It would just be in the discovery of different physics. So there's no sense of inevitability of our physics. It's a happenstance or a circumstance of the universe we live in. And in these exotic and unproven and maybe even untestable multiverse theories, there's the idea that there could be other types of physics in some part of a space-time continuum that leads to parallel universes beyond our own. So that's a sort of way of finessing the particularness of our physics by saying, well, there are other types of physics out there in the multiverse. But again, that's speculation, but it's a great question.
So we get this question from time to time, and it's shown up again. And the question is, what do you recommend that someone study if they are interested in astronomy? Like a student, how does a student become an astronomer? What do they study to become an astronomer?
Yes, to be an astronomer, as opposed to just recreationally study astronomer, like with the MOOC, that this is a live session for MOOCs, and massive open online classes are certainly a way to get your feet wet in astronomy. But to actually study astronomy at a technical level, it's hard to do that fully online. You essentially have to be part of a degree program because you're essentially getting a qualification that shows that you've mastered really not just astronomy, but a lot of physics and math. So in our undergraduate degree program in astronomy and in all the others around the country, those students, even though their bachelor's degree says astronomy, there's 70% overlap with what a physics major would take. So that gives you a sense that more than half of the courses you would take to learn astronomy at a technical level of a degree is physics. And then there's a lot of foundational math that you'd have to take through, obviously, several calculus courses, differential equations, and so on. So the simple answer is that you have to take a degree program to really learn the subject up to the level where you could say do research, work in a research group. Even as an apprentice, you still need quite a lot of technical knowledge. And those degree programs are all around the country. There are, I think there are about 20 standalone astronomy departments that offer astronomy degrees, again, often combined with physics or including a lot of physics. And then there are more, maybe 50 departments where there's astronomy in a physics department, and they're offering hybrid degrees of physics and astronomy, or physics with an astronomy specialization, and so on. So that's the simplest answer. It would be very hard to get that all remotely or online, because most of those classes, the upper division classes especially, where you start to learn about the stellar structure and the interstellar medium and general relativity and cosmology, those classes are not typically online. So even if they were online, you probably couldn't put together enough to make a full degree program.
All right, the next question is about the center of the universe. And it's generally about, is there a center of the universe, with the questioner suggesting that maybe the center of the universe could be in a different dimension. So could you talk about the universe having a center?
So in the basic cosmology that we have had verified by data starting with Hubble in the late 1920s, there does not appear to be a center of the universe, because Hubble measured, and it's been confirmed now with many times larger samples of galaxies, that all the galaxies, distant systems of stars, appear to be moving away from us, have recession velocities that increase with the distance. And the simplest interpretation of that's the Hubble law, is that if you trace that backward, then all the galaxies were in one place at one time. And we would call that the Big Bang. But the fact that the galaxies are all moving away from us does not give us a special situation in that expansion, because if we were situated on a distant galaxy, another galaxy, doing the same type of observations with telescopes, we'd see exactly the same thing. We'd still see all galaxies moving away from us. So you just have to imagine taking a rubber sheet and just scattering dots of ink on it randomly, and imagining each one as a galaxy. And if you and a friend got together and stretched that rubber sheet in 2 dimensions and imagined your perspective from any one of the dots, you'd see that all the dots around you are moving away from you, and the ones further away are moving away faster. That's what Hubble saw. But if you were on a different dot, you'd see exactly the same thing. So with the rubber sheet analogy, it's clear that there's no special position, that the expanding universe is an expansion that's global, and so every galaxy sees the same thing. Now, the second part of the question is interesting. Could this apparent no center go away if the universe had hidden dimensions or extra dimensions? And the simple answer is we don't know. But it's not obvious that it would, because the fact that we have no privileged position in this universe, in the 3 dimensions of space and 1 dimension of time, actually, to a physicist, sort of implies we have no privileged status, even if there were higher order dimensions.
All right, so Musa here asks, why does Venus spin the wrong way?
Good question. And again, simple answer is we don't know. Notice in science, it's important to be able to say you don't know, because sometimes we simply don't. So Venus is an oddball. It counter-rotates, which is to say that all the planets in the solar system otherwise spin in the same direction that they go around the sun. And so in physics terms, this means their angular momentum vectors are aligned. So the angular momentum vector of the Earth, even though the Earth is tilted 23.5 degrees, all the planets have the same spin orientation as the orientation of the angular momentum of the sun, which has most of the mass. Venus does not. Venus has the opposite orientation of an angular momentum vector because it's on its head, if you like. The question of why is we don't know. It probably didn't form that way. So it's almost certainly that it was not part of its formation process because the physics of the formation conserves angular momentum and would not lead Venus to do that. The best guess is that Venus suffered a dramatic and catastrophic collision early in its history, just as the Earth suffered a collision with a Mars-sized object that led to the formation of the Moon, maybe a few tens of millions of years after the Earth formed. A similar collision with Venus, maybe even a larger collision with a bigger than Mars type object, could have easily flipped it on its head and left it with the counter-rotating spin that it has today. But of course, it all happened so long ago that the evidence of that has long gone. There's the Venus terrain has terraformed multiple times due to volcanism, so that even if we could see through the thick atmosphere, there'd be no hint of a crater. Venus, would have reformed its spherical shape even if it had a huge chunk knocked out of it as it was flipped. So there's really no way to prove this. We can show that it's a plausible scenario with computers, and people have done that, but that doesn't mean we can prove that it happened.
All right, the next question is from a live viewer who asks, did Patrick Moore get you hooked on astronomy at all?
It's a good question, and he could have, but I actually grew up so much outside the UK that he wasn't as central a figure in my youth as he was for many of my colleagues who stayed in the UK. I was born in Scotland, and I spent the first only 5 years of my life in London and Edinburgh before moving to the States. So I grew up in the States for the most part, hence the accent has gone, the British accent, and then went back for undergrad and grad school. And of course, I did know Patrick Moore then. He had 40 years, I think, his Sky at Night, his TV show and radio shows were going for a very long time. So he was the iconic figure in astronomy through all of my youth, and in the UK for a long time, sort of the Carl Sagan of the UK, if you like. But a little different flavor. He was extremely quirky. I think he lived with his mother his entire life, until she died when she was in her 90s and he was in his 50s or 60s. He was kind of a fuddy-duddy, if you like, a sort of musty old Englishman with a love of astronomy that was very infectious. He wasn't an active research scientist the way Carl Sagan was, so I wouldn't really compare the two. But in his influence on generations of British young people to be interested in the sky, he had an immeasurable influence.
All right, so I'll ask 2 questions in a row here. The first one to give you some time to think. Somebody would like to know, what's your favorite astronomy joke? So if you don't have one right away, then I'll let you think about it.
The quick one is, when you ask an astronomer, how are things, you answer looking up. That's my quick astronomy joke.
So then Musa here asks, why do we only see one side of the moon from Earth?
So that relates to an earlier question about tidal locking. So the moon is a relatively large satellite or moon of the Earth compared to the planet size. It's unprecedented in the solar system. If you look at Mars with 2 very small moons, Phobos and Deimos, Venus has no moons. You go to the outer solar system, you have Jupiter and Saturn with dozens of moons, but then even the biggest of them is much smaller relative to the giant planet size than the moon is to the Earth. So the moon, at a quarter of the size of the Earth, is a very large moon of a planet, and it's quite close to the Earth. And that strong gravitational connection leads to tidal locking, which is to say the interaction between the 2 objects gravitationally. If the moon originally formed with a spin, just as the Earth spins once a day, that spin would gradually be degraded until it is gripped, essentially. Just think of gravity gripping across the 250,000 mile distance, gripping the moon so that one face always points to the Earth. And the same is true in other situations. Mercury is the closest planet to the sun and is quite small compared to the sun, and the sun's grip on Mercury causes it to be tidally locked, and so the Mercury's same face is always facing the sun. So it's a quite general phenomenon that occurs in the solar system and presumably in other solar systems too.
All right, the next question is from a live viewer who asks, have there been any new findings about dark matter this year?
Well, this year, the big question about dark matter hasn't been answered, which is, what is it? At this point, we know of dark matter in so many places in the universe, and as I mentioned to an earlier question, we have thousands of images of gravitational lensing, each of which is a demonstration that dark matter exists in galaxies and clusters. So the existence of something that we would describe as dark matter is beyond doubt. And the evidence, just piling on more evidence like that, is not really getting us very far. It's not really helping us. The big question now is what is the fundamental physical nature of dark matter? And that wasn't answered this year. So I would say this year we didn't make any dramatic progress on dark matter. The physics type experiments taking place for the most part in deep mines shielded from cosmic rays, where we're looking for the very rare interactions of a hypothetical dark matter particle, subatomic fundamental particle, with a large detector, a solid state detector of some pure material like germanium. Those experiments have not yielded success yet. And the fact that they haven't detected that particle after now, for some of them, a couple of years of operation, is starting to be a problem. In a couple more years, if there's no success, then physicists will have ruled out a couple of their favorite candidates for the dark matter particle. And at that point, given that the process of elimination has excluded everything else from black holes to substellar objects to Jupiters to pebbles or rocks in space, astronomy and physics is going to have a big problem. But at the moment, it's a waiting game. And so, if you like, it was a rather dull year in dark matter.
All right, Rami, who is online with us, asks, what is the star that was seen by the three shepherds when Jesus was born?
I don't remember the name that astronomers have given it, and it's not completely, this is not a completely nailed scientific mystery, but it was a supernova. So the speculation was that a supernova, so the best accounts, biblical accounts are not direct. They're not direct eyewitness accounts from 2,000 years ago. They were passed down, transcribed dozens, sometimes, of course, hundreds of years later. And so to assign an astronomical event to the Star of Bethlehem requires knowing exactly where it was in the sky and when it was observed and from where. So the from where, that's understood. Nobody doubts where Bethlehem is, and that part of the Middle East, it described in biblical stories, is well understood. And the time frame is generally well understood too, because there are other references to situations of agriculture or shepherds and flocks and where the flocks were. So there's enough sort of indirect evidence of the time of the year, but maybe not even an exact date. So the exact date is actually up for dispute. I think I've seen research papers which assign 2 or 3 different dates to the appearance of this star magically in the sky in the east. So unfortunately, we don't have enough information to tie it down to an astronomical object. Also, if it was a supernova that appeared momentarily, for a week or so at maximum light and then faded, we would hope to be able to see contemporaneous accounts from other cultures. The Chinese were keeping good star records, also in the northern hemisphere. So we would expect any equatorial or northern latitude civilization or culture that was keeping astronomical records, or even doing rock art or whatever around that time, to have made a record of it. Now, it's conspicuously absent from Chinese astronomical records, which is a little suspicious. So the supernova assignation to the Star of Bethlehem is controversial because it's not an open and shut case.
All right, the next question from, again, a live viewer is, why is the L2 point the best place for the James Webb Telescope? So
the Lagrange points, L2 is an abbreviation for the second Lagrange point. The Lagrange points are gravitational balance points. So when you have a sort of a gravitational system, Earth, Moon, Sun, for instance, those three objects, there are places where the balance of gravity is maintained. And so you can keep an object in place while only giving it a very minor perturbation with a rocket. So that's a very attractive thing for a designer of a space observatory or a long-term space habitat or something, because you can use the gravity of the objects and keep it in a fixed location with minimal expensive rocket fuel. Now, not all Lagrange points are stable. Some are stable, some are unstable. L2 is advantageous because it's on the far side of the Earth from the sun. So you can be shielded from sun's radiation and also further from cosmic rays as well. So the sun's radiation is a bit of a problem sometimes, especially during solar storms. So the L2 point is favored not just for James Webb Space Telescope, but for a number of space missions. Could even start to get crowded at L2, given what the Europeans, the Japanese, maybe eventually the Chinese put there. The downside of having something, that's in a very quiet space environment, which is the real reason you do it, is that you're far enough away from the Earth, 50 million kilometers, I think, from the Earth, that is completely unserviceable. So once James Webb is put at L2, it has to work. There's no way you can fix it, as the astronauts did with the Hubble Space Telescope 5 different times. So James Webb is a very high-stakes space mission. Its cost is well over $8 billion, close to $9 billion. It's going to go up after a recent delay. There's a collision in the launch schedule, not a real collision, but a collision with the Europeans who own the launch site, and they sort of trumped NASA on the launch date. So it slipped from October 2018 into early to mid 2019. And I think it will go at that point because the cost overrun will just keep stacking up if it doesn't go. But once it unfurls its large mirrors and deploys its instruments and switches them on, that's it. The thing will work. And if it doesn't work, it's a very expensive piece of space junk.
All right. The next question is from an email who asks, what is expected from quantum computers in the study of astronomy and cosmology?
Well, quantum computers are going to help every aspect of numerical astrophysics. They'll have an impact on every field, just as they will have an impact on weather forecasting, on all of the modeling that we do in fields outside science or outside astronomy. So quantum computers are supposedly going to keep the progression that was sustained by Moore's law, by the increased miniaturization of electronic components and switches and integrated circuits. That's been sustained for several decades. Quantum computers potentially will keep Moore's law going another few decades, which is a phenomenal thing because you're doubling the processing power or per unit area or per time every 18 months. Quantum computers will let astronomers do calculations that are really challenging now. So that would be simulations of the entire universe where you're modeling every single galaxy. That would be especially general relativity calculations, which are extremely difficult. You're solving the equations of general relativity in a highly variable gravity situation, like modeling gravitational waves, colliding black holes. Those push existing supercomputers to their limits. So quantum computing will help with those gravity calculations, will help with simulations of the universe, will help with simulations of extreme astrophysics, such as a supernova, such as the extreme astrophysics that happens in a fraction of a second where a star collapses almost to a point and temperatures raised to billions of degrees. It's extremely difficult to do in a computer. So quantum computing will move astronomy and astrophysics forward a lot if it happens, which it seems to be happening.
All right. The next question is from Muzahir, who is on with us live, who asks, is the multiverse real?
Not as far as we know, and it may not even be testable. So the multiverse is a theoretical construct that that seeks to go beyond the standard Big Bang, where the Big Bang is the beginning of all time and space and essentially all we can talk about in science. And in conventional Big Bang cosmology, a veil is drawn over our knowledge at the time of the Big Bang, this state of infinite temperature and density that we really can't understand without a quantum theory of gravity. Well, the multiverse ignores the veil that really we draw over the Big Bang due to unknown physics, and speculates that maybe there are other space-time situations, maybe with higher dimensions, more dimensions than the 3 of space and 1 of time that we know, and that would be like string theory or brains. And also speculates that there are potentially other space-time entities out there where the laws of physics are different, where the dimensionality of space is different. They're really unrecognizably different from our universe. The trouble is, in the simplest framing of the multiverse, these universes, these other universes, are not really observable by us. It's possible they may have an indirect imprint into our universe through, for example, gravitational waves. That's an area of active research, but nobody's demonstrated how you would show a multiverse exists through gravity wave detection, even if we could detect that kind of gravity waves now, which we can. So I would say the multiverse sits firmly in the realm of speculation.
All right, and then the final thing that we'll talk about today is what do you think were the most important astronomical discoveries from this past year and why? A year in review. So
year in review, well, I think the TRAPPIST system, I mean, I might put that at the top of the list. That happened early in the year. But the TRAPPIST system was extraordinary to find 8 planets, which is, so that's as rich as the solar system. Since Pluto has been demoted, we have an 8-planet system. And 3 of those planets were Earth-like or quasi-Earth planets in the habitable zone of their star, their lower mass and red star. So that was extraordinary to find such a rich solar system with 3 habitable near-Earth planets in one go, and the subject of much future discovery and discussion. The other, and these are competing for each other. I don't know how you put one above the other, but obviously the other, the first gravity wave detection was not this year, that was last year. But the first neutron star collision and the birth of what's called multi-messenger astronomy was this year. And that was extremely exciting. That's the birth of a whole new field of astrophysics. So to review, the gravity waves were detected previously from the mergers of black holes, where the only signature you get, because black holes are invisible, is the gravity waves themselves. But when neutron stars collide, there's a lot of astrophysics that happens. The neutrons, some neutrons are flying out of the system at relativistic speeds. They impregnate the gas surrounding. They pump up enormous numbers of heavy elements, create heavy elements by neutron injecting into the nuclei. And so the neutron star collision that was first detected and followed by 60 or 70 telescopes on the ground showed an enormous surge of gamma rays, and so it was a gamma ray burst and partially explained that phenomenon. It explained where a lot of the heavy elements in the universe came from. It showed how we could use a combination of gamma rays and X-rays and optical telescopes to localize the source of a gravitational wave event, which had not happened with the previous events. So that was a profound and dramatic discovery. And I think those two, there were other things that happened, but those two are sort of head and shoulders above everything else this year. So those are good questions to finish the year off. We'll be back in a couple of weeks. The American Astronomical Society has their biannual meeting, and the one in DC in early January is the biggest one, probably 3,000, 3,500 astronomers, and Matthew and I and other people in our group are going to be there. So we'll be taking a few weeks off, and we'll be back in the middle of January. And everyone have happy holidays. Goodbye.